Hello and welcome to another hands-on engineering video. In this video, we'll discuss the SPI protocol and demonstrate reading registers from a typical SPI-based sensor. SPI stands for Serial Peripheral Interface. It is a synchronous serial communication interface, which just means that we use a clock to standardize communication and send bits out one after another. SPI is most useful for very high-speed transfers over short distances. Let's compare it to some of the other serial communication protocols that we've covered. Links to our videos where we cover I2C and UART are in the description below. We can see that SPI needs more wires and operates at much smaller distances, but also provides extremely fast data transfer. I2C and UART both only require 2 wires, and the trade-off between the two is speed versus distance. UART is preferred for larger distances where speed can be disregarded, and I2C is where speed is required over a smaller distance. SPI doesn't have a formal standard to describe how data should be encoded over the lines, so we typically need to resort to reading datasheets for the sensors that we are interfacing with. That said, there is a typical way to read and write to a sensor register over SPI, and that is what our example later will cover. We will have one master, like our Arduino microcontroller, communicating with many slaves, or the sensors. Onto the interface itself. Typical SPI devices communicate over 4 lines. These lines are master in, slave out, or MISO, master out, slave in, or MOSI, SCLK, or serial clock, and slave select, or SS. The clock is generated by the master and serves to synchronize everyone communicating over the bus. At a high level, the master draws the SS line low for the slave that it wants to communicate with. Then, data is sent over the MOSI line towards the slave. If the slave has something to respond with, then this data will be sent over the MISO line. When communication with the slave is over, the master will pull the SS line high, thus releasing the slave. The specifics of when data is sampled over the lines depends on what SPI mode we're using. SPI modes are made up of combinations controlling the clock polarity and the clock phase. What this means is that we need to choose whether the clock idles at low or high, and whether data is sampled at the leading or trailing edge of the clock. In this diagram, CPOL represents the clock polarity, and CPHA represents the clock phase. We see that at CPOL equals 0, we have a non-inverted clock where the clock starts out low and pulses high. CPOL equals 1 is the opposite. The clock starts out high and pulses low. The dashed red lines represent the leading edges of the clock, and the solid blue lines represent the trailing edges. We see that depending on when the data is stable and when the data changes, we have to adjust our clock phase. At a clock phase of 0, data is stable on the leading edges and changes on the trailing edges. At a clock phase of 1, data changes on the leading edges and remains stable on the trailing edges. Ultimately, we have to respect whatever requirements the slave or master have. Since we have 2 settings with 2 options each, we have a total of 4 SPI modes. The reason we have all these modes is because, as mentioned before, there is no standard for SPI, and so we have to be willing to adapt to any master or slave requirements. Now let's go over an example. Here I have an RFID sensor called an MFRC522. The device only supports SPI communication, and as mentioned before, it uses the most typical SPI reading or writing format. The Arduino uses an AVR microchip that provides dedicated SPI communication hardware with certain pins dedicated to be MOSI, MISO, SCK, and SS. Since these pins vary in location by board model, they are also tied to an ICSP header, which are on the 2x3 grid of pins at the edge of the boards. On the Nano model, which we will be using, pin 10 is SS, pin 11 is MOSI, pin 12 is MISO, and pin 13 is serial clock. I've wired up these pins to the corresponding pins on the sensor. Pin 13 also happens to be tied to the built-in LED, and some sensors operating at high speeds may have issues because of this. There are some mentions online that removing this LED may help in these cases. There is a register in this sensor called version reg, which returns the firmware version on the sensor. What is on the screen right now is the code to read this register. Firstly, I define a variable for the version register's hexadecimal address. Then, I define a constant for the SPI settings. The datasheet describes how it wants us to sample relative to the serial clock, and using this, we know to use either mode 0 or mode 3. The datasheet also specifies that we should send data most significant bit first over the lines. In the setup function, we call this method readRegister, which returns a byte of data and takes in a byte address for the register. Going down to this method, we see that first we tell the SPI library to get ready for a transaction. Then, we see some corrections that need to be done to the address specific to this sensor. In the datasheet, it says that the least significant bit is always 0, and that the most significant bit determines whether we are reading or writing. I want to stress that this is specific to the MFRC522, and I am only showing this because I want to emphasize the importance of reading the datasheet for the sensor that you are using very carefully. Next, we draw the SS line low, which will tell the sensor to get ready. The datasheet also describes which order the bytes are meant to be sent and received. We see that the sensor wants us to send our address out of the master at byte 0 and to ignore what comes in at the same byte from the slave. Then, on the next byte, we can grab the data that we requested on the previous byte. We can also end reading by sending out 0x00. Finally, we draw the SS line high and end the SPI transaction. When we run this code, we see the hex value 0x92. If we look at the datasheet for the sensor, we'll see that the first value is the chip type and the second value is the firmware version. So, we have successfully read the version register. Alright everyone, that's it for this lab. We hope you enjoyed it and learned how to use SPI in your projects. If you did, make sure to leave a like and subscribe to our channel. Feel free to leave recommendations for future videos or things we can show in our videos in comments below. That's it for Hands-On Engineering. See you next time.